varied from individual to individual.
Yeah.
And how many have you interviewed so far?
You're the fourth.
Okay. So I think one, they're going to be really varied. And in fact, you can ask the same person, 1 month later.
Oh,
and
you think?
You might get... look, I haven't... I have to perhaps see hear the questions first. Right. But I would imagine that you're also going to get a bit of variation.
Interesting.
Because there are nuances that somebody would then say, oh, well, actually, now, I don't typically think about this, but now that you asked me, a month later, they say, I've been thinking about it, or it come up again in another context, and I realized it was related to something that you asked me, and I now have thought about it in a slightly different way, and I think this or that. In other words, sometimes people do things, for example, like riding a bicycle, and when you ask them, well, how do you do it? Right. Why do you do it? They might tell you that, and then afterwards go, actually, that isn't how I ride a bicycle. I gave all these misleading things that I do, so that's I think what I'm getting at. That unless these are things that I've really thought about before, or people like myself, they might evolve once they start to think about them.
Yeah, that's absolutely true. Well, you can tell me after the interview. I would love to know.
So maybe I'll just go through a whole lot of yes, no.
I hope not, because they're not quite structured that way.
Okay.
But so I'm going to be asking you some questions about what you think science is and how it works. And these questions come from an interview that has been given to students. So just keep that in mind when you hear them. If they sound you're not really sure exactly what I'm asking, just tell me that, and I'll try to rephrase it till it makes more sense, if it doesn't make sense. And also, of course, there are no right answers. I'm just wanting to know what you, as a working scientist, think about these topics. And I'm going to ask the questions. They're written in a certain order, but if at any point you feel like you've already answered a question I asked previously, just tell me that and we can move on. I just need to ask the questions in the order to keep the protocol.
Okay.
And it should take about 30 minutes or so. Is it okay with you if I record it?
Yeah, I thought we were.
Yeah.
Okay.
And I won't share your responses with any of your colleagues. Your name won't be associated with your responses or the study.
No, you won't tell them. There's no way he can be a good scientist, given what he just told me.
No. And if it's published, your name won't be associated in any way. And of course, if you want to stop the interview at any time, we can. Just let me know. And do you have any other questions?
No? Don't think so. Of course, I'm eating my lunch. So.
Oh, well, that's all right.
So as long as you think the recorder can hear me, we're happy.
I'm sure.
Okay.
Yeah. We can just put it right here.
Okay.
So my first question is, what do you think science is all about?
Well, at one level, it's really about trying to understand things and discover things. And there's a feedback there between the two, understanding and discovering. But along with that will come with trying to create a conceptual framework to put the observation in a context that is self-consistent, at least self-consistent to what humans perceive as self-consistent. So then, through the observation and discovery process, there comes model building in terms of then having models that are predictive and then testing that. And if the tests are passed through experimental or whatever it might be, calculation, then the theory gains additional credibility. There is also, at least nowadays, the additional factor where science is funded for the benefit of the society. So there are many different types of research, and some of the research, instead of being as general as I've just outlined it, it can be also very specific in terms of, if there's water that's polluted, then what would be the best ways to treat that water, and so talk with chemists, etc., about that particular problem or get advice. So there the research is then very goal-specific to a medical problem. But even within that specific goal-oriented research, there would still be models and proposals tested by experimental observation and validation, or the model not being valid and experimental observation showing that.
And so you spoke a little bit about goals, but what do you think the goal of science is?
You mean, are you getting at that there is some sort of overlying or overarching goal?
Or maybe, is there?
The origin of science is really it's philosophy, except that it's now very distinct from philosophy in that science has to be, it's hand in glove. When we say science, we really mean experimental observation. You cannot, it's no longer acceptable to just come up with hypotheses and models and not think that one needs to verify it. So there was a time where, if you go back far enough in science, in the history of science, where people were quite satisfactory to come up with models, and if they sounded very logical and self-consistent, then they must be right. And therefore there wasn't the whole idea of actually proving a model, or at least gathering some data to have experimental observation to validate or refute a model, was sort of it came later on. In terms of the overall goal of science, I'd say a lot of science nowadays is driven and funded for, as I said, medical benefit, industrial benefit. I think what you might be getting at is the more romantic notion that, and which would play a role in people who are not practicing in the field of science and research, where science has some goal in terms of understanding. This is going to get tricky now. Understanding self, understanding how the mind works. So now we have a branch of science, neuroscience, etc. But when you say the word science, it must be understood now that when I hear that word, I'm going to say that psychology is science, because what psychologists do, and what now most fields do, is they have various models and they test them and they validate and they collect data, or they have just outcome studies where, if you're a clinician, you may have a very vague model as to what is going on inside the body, but you do clinical trials, and that is pure empirical data, and from that you gather statistics that then say, well, yes, actually this medication is of benefit. There are some side effects, but it has helped with a particular disease or condition of the patient, and therefore it's worthwhile. So that is a purely empirical type research. So when you say science, psychologists do that in terms of treatment. What treatments work, why don't they work, or when would they work, in what context, is some treatment perhaps better than another treatment, or age group, or even a socioeconomic group, etc. So I'm a little hesitant when you say the overall goal of science. I just see science now as really an empirical observation backed up with rational thought, where things have to be validified or disputed, or if it's not clear, then that is part of the discussion too, in terms of the outcome. If the observation is not clear what it means, that has to be discussed as well. I think if you're using the context of this word science, and the person who hears that word then has this very romantic image of being somehow different from what psychologists do, or what I want to pick, or economists do, or just as a side one, the data in economics is very noisy, and so it makes it very complicated. But of course, there's many economic models, and some of them highly sophisticated in terms of their mathematical sophistication. So therefore, that is science. So now I'm including economics as part of science in terms of testing and validating. But if you're going back to this romantic notion of science being some higher goal of understanding things like what makes the human species different from another species, if there is some higher state of being, or perhaps even then going on to consciousness and religion and that sort of thing. I'm not sure I have that much to say about that. I don't know. So, am I correct in that you're sort of angling in terms of the science?
I want to just hear what you personally think the goal is, and so however you define science, the goal of that is what I want to hear about.
Okay.
So thank you. No, you definitely answered. So what do scientists do, or how do they achieve the goals of science?
Well, that I've probably covered perhaps in more detail than perhaps answering the original question. I'm not sure. Because what they do is they have a model and they test, and they discuss, and everything gets slightly modified, updated, and refined. But I can certainly see, I think, going back to the previous question, what is the goal, right, of science? Whether these goals are actually achievable, but one could imagine, because they're related to politics, etc. But no serious diseases, being able to deal with viral and bacterial diseases, at least as a start, that there would be a wide range of medicines that would be able to deal with all of those ailments that can cause death, sickness and death. I think one of if you spoke to an astrophysicist, they might say, "Well, gee, of course it's obvious. It's understanding the origin of the Earth. That has to be the biggest goal." And if you spoke with a physicist, being particle physicist, they say, "Well, of course, we've got to understand the fundamental laws of nature." And so I haven't mentioned that. In chemistry, we do that to some extent, but we do it more at the molecular level and the atomic level. And of course, that has then all sorts of implications for applications. But in terms of, one of the goals of science is to understand the world around us in terms of what we call natural laws, be it the law of gravitation or properties of light, because we're inquisitive beings and we want to understand why a certain surface will reflect an image and another one won't. Just starting with that. And so it's to understand the natural world around us. There's a very strong driving force. I just think that nowadays the bulk of science is, yes, there is that going on, but a lot of the time now it's geared towards a particular outcome, particular application, a new material to do with the semiconductor industry, or a new material to do with certain properties that are being looked for because there's an interest. And a lot of it is also trying to make a new material that'll have new properties that have never been observed before. And through that, you then understand or have a better understanding of the material world around us.
So, do you think scientists ask questions?
Yeah, all the time. The daily job is nothing. You have to be very critical as a scientist, so that you can figure out that what you think you're observing is what you're observing, and the way you're interpreting it is a reasonable interpretation. So yeah, you have to question all the time. I mean, that's really one of the characteristics of science, and that's why I've broadened it to say, I include economics and psychology, etc.
So what kinds of questions do they ask?
How can I get funded? Okay. That's a negative comment. You can delete that one.
That may be
within
honest.
that context. No, but within that context, sure, things have to be feasible. No point coming up with a research agenda that is beyond, is costing hundreds of millions or billions, whatever. Your question, what type of questions do they ask? You said, do they ask questions? Yes, they have to. What time? It's the nature of of the job, of the activity.
And so what sorts of questions do they ask?
Well, that is the answer to that is, it depends who you're talking to. Depends what field they're in. I mean, is the question asking specifically, like what?
You can answer it specifically, or you can do it generally, whichever you would prefer.
I mean, that is so wide, because if you get to specific questions, it's just related to the particular project or thing they're working on. But general questions that would be in common. What experiments can we do to narrow down the answer to a question? In other words, what would be the most efficient way that if we're trying to solve a problem, what's the most efficient way to do it? And so to come up with a set of questions and experiments that would answer that unambiguously, at least hopefully that would be the goal, that would be an unambiguous then outcome if they had this data. And so then they go about figuring out how to proceed with the experiment, and execute it, and then analyze the data. So I would say efficient hypothesis testing and data collection, very important.
They would ask themselves if this was efficient or not.
Yeah.
Okay.
What would be the most critical things you could do to narrow down the options, or to, in other words, to get the clearest answer for yourself and whoever else is working on that project as to what's going on. And then once they have narrowed down some of the big questions, then go into some more detail. But a particular researcher may or may not do that. They might say, I now understand this, I'll publish it, and they'll leave perhaps the more detail-oriented work to somebody else, or to somebody who has a particular application in mind, that sort of thing. So efficient hypothesis testing is very important. And of course they're going to frame their questions, their hypothesis, that is either going to be self-consistent with what is known, or if they suspect that what is known is perhaps misleading, then they're going to directly challenge that and see, can they design an experiment that is an efficient one that will very clearly answer that. Is it really occurring the way we think it is? And either get an answer that refutes that or modifies what is already known or supports it.
So that's how they answer their questions? They set up an experiment?
If you're an experimentalist, yes. If you're a theorist, you would, which I am not, but they would analyze things and see if there are new relationships and publish those new relationships. And then others, i.e. the experimentalists, would be then tempted to then validate or refute that new proposal, that new equation, that new suggestion in terms of relationship between two variables or two parameters. which can be observed. I'm saying it in a very simple way.
Yeah.
But yeah, so they would a theorist might come up with an insight that would be of benefit to the experimentalist in terms of understanding their data or understanding what's known at the time, or provoking the experiment to say, that is such an interesting idea, we need to follow through and see, is that really the way it is, or is it different?
And so could you give me an example of a question a scientist might have, and then how would you go about, how he or she would go about answering the question?
At what level?
Sorry, you mean what level question or what level explanation?
Yeah, both.
Okay.
Both. I can give a general. Let me give a general one.
That's great.
I'll give a general one.
Or you can do one from your work if you want, whatever is more comfortable.
I'll do a general one.
Okay.
You take carbon atom. Its most common form is when it's bonded in a three-dimensional structure to other atoms. In fact, carbon atom is the basis of organic molecules and bioorganic molecules, etc. Of course, there are other atoms, oxygen, nitrogen, and hydrogen, would be the other main atoms in biological and organic molecules. But if you're looking to see what unusual structures carbon can form, and maybe some of these unusual structures might show up in unusual natural products in plants and frogs and whatnot, which we don't know about. That is the details of those unusual compounds. But somebody says, well, let me try and see if carbon can perhaps form a structure which is different from what it typically does, and it bonds to only other carbon atoms. And so what you have, I'm not necessarily saying this is how they did it, but what, 50, maybe 20 years ago, there was a discovery really of and the structural elucidation of a new structure of carbon, the C60, the buckyballs. And that is now a whole area of research that's related to nanoscience, etc. So what you have there is a structure that essentially looks like a soccer ball. Okay, so it's like a round soccer ball, except it's a carbon structure. Of this shell, like the shell of the soccer ball is just the shell of carbon atoms. So now what you would do is say, well, first of all, can we get some sort of closed shell structures? That is, any kind of shell structure that would be, maybe it's a tube, maybe it looks like a cigar, maybe it looks like a football as opposed to a soccer. But you realize you've actually got this thing, and then you figure out the structure. What is it? Well, how many carbon atoms? There are 60. So it's 60. It's circular. And then you start to look at the properties of that, not the carbon atom, because you've already done that in terms of the structure, but you start to look at the properties of the entire structure, the whole soccer ball structure, the C60 molecule. What are its properties? What are its characteristics? And so this is been a very active field of research, and then from there you go, well, wait a minute, this is a new structure. What can we? It perhaps could be useful for this or that, and so then you start to modify it slightly, and you say, well, our goal actually was just to have a carbon structure that was different. We've done that, but now let's modify it. Let's change some of the carbon atoms to a different atom, and see if it gives that entire structure different physical and chemical properties. And of course people have done that. So now there are applications for C60 carbon structures. 20 years ago we didn't even, who would have thought there would be applications? What there are, and that's how it evolved. So the the questions will evolve with whatever the topic is. From one, can anyone imagine a structure? Or sometimes it's the observation that comes first. And the tools, the scientific tools that allow us to determine the structure of a molecule open up completely new insights, i.e. a new structure that hasn't been seen before. And then from that a whole set of questions come about. Well, why is it forming? Why is it stable? Or why is it not as stable as the other structures? And then possible applications. Given its novelty, how different is it? Well, if it's different, then maybe it could do this or that, etc. So there you've now got, from that you've got what's called nanotubes. Nanotubes, at least if you're using a carbon framework, are going back to really the C60 structure, but now you're changing the conditions where you can get tubes of carbon. And if you've got a tube of carbon, well, then maybe you can put stuff in the tube. And so now you've got a way of creating essentially wires that are covered in this carbon layer. Maybe you can even have a new kind of material that, if you have a whole lot of these carbon tubes, you'd have a super strong, essentially a fiber. So does that answer?
Yeah.
Okay.
Yes, thank you. So can you explain to me what an experiment is?
What an experiment is? It is planning ahead of time of first figuring out what the question is, and seeing then what tools you have available to best answer that question. And then you're going to zoom in and have to know the limitations of the equipment, and what type of results you're going to expect, and then do those experiments and see what results you do get, and whether those results are what was expected or if they're different, and if they're different, why, and that in turn can then lead to a whole lot of new questions. So an experiment is about planning, execution and data collection, and then data analysis, and then replanning, modifying the concepts that were initially you went into the project, and then you realize, well, wait a minute, we now have more information, and we realize it's actually more like this as opposed to the original thought. So it's an experiment is really, for me, data collection and analysis. But you can also do numerical analysis, so you don't actually do experiments, but you can have a hypothesis and then do a whole lot of numerical analysis, or some people might say simulation, and see what sort of an answer, what outcome you get. But the bulk of it is really experimental observation, physical observation through equipment.
Okay. So then, why are scientists doing experiments? Why?
Well, again, the curious people wanting to ask questions and get answers. If you're not curious, then game over. Do something else. And I think at some stage of some scientist's life, and what I mean by that, probably the early stages, there is the belief that you are part of a process that is about understanding the truth, as opposed to, let's say, political maneuverings, where it's all, I won't say all, but there's a lot of posturing and smoke and mirrors, and the truth is lost in the smoke. Who actually wants to hear the truth? That's not what It's not the objective. Whereas in science, it is. And so it's very critical in that sense that it's highly unlikely that something that is really incorrect, wrong in terms of model or data or experimental outcome will sustain itself. And so with time, those concepts and things that work will gather momentum, and they'll be built upon. And so with time, there is the implicit understanding in the sciences that, and here I'm being specific now to when you say it's sciences, physics, chemistry, engineering, etc. But I would say the same. I would include psychology there. I would include models of education there. I would include economics there, although economics very difficult topic. There really is an implicit understanding that you're doing it to get the answer, the right answer. And of course, within that context, in terms of day-to-day and week-to-week activity, you also have to work on things that are then, being funded, etc., etc. But it's really important for people to realize, because I think if somebody knows nothing about science, they might think, oh, it's something done by somebody else, and we can't really trust these people because they could be just making it up. And people are too individualistic. It doesn't matter what branch, if you've got any branch of any field, if it has a foundation of critical thought, active discussion, open discussion, then the things that turn out to be not such good ideas or not quite as good as others, they're going to fall by the wayside. And it's highly unlikely that there's going to be this huge field of knowledge that is, for lack of a better word, bogus. Whereas there can be, once you get to the society type level of programs, or be it political programs or military programs that are just they're not based on any critical or open discussion. So that is always a reason, I think, for why somebody would or should go into science, where they feel that even if they're just doing one very small thing, they're going to be supported. Might not feel that way, but if they feel that there is something, whatever they're working on, and something is wrong, their voice will be heard. Now others might object with this pride and prestige and say, this paper's bad or this work is bad, but it does essentially get out there, and especially with the open communication that we have nowadays, it gets out there and somebody else is going to test it. And if they get the same result, it's going to come out. It just might take a bit longer if it's not within the established norm, but it will eventually come out. And that is, I think, an implied hypothesis that science is willing, that the truth will emerge. It might be messy. It might take a long time. Some people's careers will not do well, and others will do better than they should have, because they were good political animals, so to speak. But within all the variation of human characteristics and downfalls, there is still the idea, and I agree with it, that but although it's messy, the truth does come out, because whatever doesn't work. People aren't going to waste their time on something that doesn't work.
So when you say the truth comes out, do you do an experiment and then you know the truth about something, or is there more to the process than that?
Well, you can pick a very simple example. Somebody says, I think the structure of let's pick the example of DNA. Well-known example. So Linus Pauling, very well-known chemist, extremely smart, extremely bright, and had many very good ideas that contributed to chemistry. But like most creative people, hey, not everything is good. Not everything is, and he would, if he was sitting here, I'm sure be fully accepting that based on the information he had, he came up with a model of DNA, structured DNA, that in retrospect was completely wrong. Okay? But he also came up with structures for other things that were completely right. Somebody else came up with a different structure for DNA, and those two people were Watson and Crick. That structure, that model of the structure, I should say, turned out to be correct.
And how did they figure?
By experimental data.
Okay.
By experimental data and getting more data and refining that, and basically getting the structural data to figure out what is the structure of DNA. And with that comes with developing tools, because a lot of the time it's the tools that allow one to in the sciences to really answer a question. So here you have a scientist who's extremely well known and well respected, and comes up with a model, and it's wrong, and that isn't the emphasis of science, but it clearly was refuted, and the correct model is what gained momentum, and then a whole lot of experiments, and now millions and millions of experiments have corroborated that structure, because everything else is fitting in terms of what we know, in terms of bonding and structure, etc. So even though we cannot physically see it with our eye, we see these things indirectly through machines. Every time somebody tests and say, well, really is the structure like that, they'll do something to test that. And they'll get an answer that says, well, it's self-consistent with that structure. There can be times where people can mislead themselves into thinking it is self-consistent, but again, there'll be a paradigm shift, and that's what happens in science sometimes. But even then, when Einstein came up with new laws, they didn't make Newton's laws invalid. Newton's laws are still valid. They're just valid under a certain set of conditions. And Einstein's equations are valid under a different set of conditions. So in a chemical reaction, mass is not converted to energy. And so saying conservation of mass is entirely correct. But when you have a nuclear reaction, their mass, at that energy scale, mass can be converted to energy, and therefore the conservation of mass doesn't hold. All you have to do is modify and say conservation of mass energy. Because now the two must be a constant, in the sense that mass can be converted to energy or energy to mass. But you cannot just have either mass or energy appear or disappear. There's no magic here. You can't. And so people, would say, really, let's test that. And if somebody can really show something, and it has to be verified by others and confirmed. As I said, individuals all around the world, and they're curious and sometimes aggressive and sometimes protective and whatever, and they hear an idea, they're going to test that and they're going to pursue it, and if it's valid, they're going to be publishers saying, yeah, this is what we find, and we've added our bit to it, and if others find that it is not what others think, they're going to publish that too. So again, that really is what the scientific method is about, having an open discussion and experimental observation that to a large extent determines what is going to be accepted. There are, of course, but even in astrophysics, there can be some very sophisticated models that at that particular time are not testable, but then they are testable 20, 30, 40 years later. And that's happened throughout all branches of science. So people came up with complicated models to describe how the Earth was the center of the universe. And and other creative people said, really? Why? And started to make observations, and from their understanding started to say, well, it doesn't look that way from what we can see of how the other planets move and the stars and whatnot. It kind of looks like we're not in the center here. And of course, if you're part of a dogmatic society, i.e. the religious society, heresy. God said Earth was the center of the world. You are therefore evil. In science, there isn't evil. There isn't. How it's applied might be evil. I mean, Einstein isn't evil. All of us. I don't want to just pick one scientist, but Max Planck or Werner Heisenberg. These people are not evil because their work contributed to the understanding of converting mass to energy, which is the basis of an atomic bomb. They didn't. Their objective wasn't to build bombs. That was the furthest thing they were thinking. But in the same reason, I can have a knife here that's a very useful tool, and I use it all day long not all day long, but when I eat, okay? But I can also, somebody else can use that knife to stab somebody to death, right? So are we going to say, well, whoever invented the knife is a bad person, right? That's not the case. So, but I think we got off the topic somewhat.
That's okay, it was interesting. So when we were just talking about experiments, but how does one decide what experiment, as a scientist, how do you just decide what experiment to do?
A lot of times, very practical reasons. Very practical reasons. You look at, again, what's going to be the most efficient. You look at the skill sets of your own skill sets and those that are working in your group. You look at your resources. What equipment do I have? Or will I have access to, or could I get access to? And if there is something that you can do, but you really feel like there really is an experiment that you don't have the equipment to, then you collaborate perhaps with somebody who does. And you try and get them interested to say, well, look, could we do this joint thing? It's not your main objective, but it is mine. But you're the expert in this equipment and this particular type of experiment. Can my grad student work in your lab? And so there's a sharing of resources and ideas, etc. So it's one, what's going to be efficient in terms of answering questions. Two, what are the tools I have available to then implement that efficient question and answer process? And then three, then there's practical things like, well, do you have a postdoc, do you have a grad student, or do you have an undergraduate? Because their skill sets are different. And what time do you have available to supervise the undergrad versus the postdoc? The postdoc is going to be up and running far quicker than an undergrad. And so you're looking at your resources, and I mean resources, your time resources, your other obligations, teaching, etc., and your resources that you have available either in your own group, in your division, in your department, at your university. If it's not in your university, but universities nearby, and if that isn't, you keep going further out.
Okay. So you mentioned hypothesis before. Can you tell me what the hypothesis is? Explain it.
Hypothesis. Well, if this molecule, I'm going to have a very simple example. If this molecule is what we call polar, to a chemist that means the electrons are not located symmetrically in the structure. It's a very broad definition. I don't want to use. I'm trying to stay away from science. A lot of jargon.
Okay. Thank you.
So, if a molecule is polar, then, generally, molecules that are polar are likely to be soluble in water or at least other polar solvents. So you can, one, either determine the structure of that molecule so that you know the location of all the atoms and what type of atoms. And if you know the type of atoms and their location, then you'll know whether that structure is polar or not.
Okay.
Or, that can take some time. The structure can be complicated. Or, you can take some of that substance and see if it dissolves in water. Or in a polar solvent, or which solvents does it dissolve in. And if it is soluble in water or other polar solvents, then it's likely to be polar.
Okay.
That would be a hypothesis testing.
Okay, so the hypothesis is...
If it has this structure, it should be polar. If it's polar, it should be soluble.
Okay. And then you test it.
The experimental observation is this, what we call solubility. Does something dissolve in a particular solvent? In the context of everyday language, they usually imply water. So, for example, oil is non-polar. It doesn't dissolve in water. So there's your simple outcome. In terms of the models, it relates back to structure and the atoms in that structure and their location. So it gives you some insight to what type of structure that could be before you've even tried to look at the structure. You've just done a simple test, you've taken that compound and you've seen, is it soluble in water? If it isn't, that already tells you something. It's going to tell you something about the properties of that molecule. That's a simple hypothesis.
Thank you. Do you think a scientist's ideas influence the work he or she does?
Say that again?
Do you think a scientist's ideas influences the work that he or she does?
I would find it hard to say that doesn't apply to everyone in every field, whether you're a carpenter or whatever it is. So the answer is yes, but I think I have to have a follow-up question that is, what do you mean by ideas?
Right.
Because thought process, it's gonna be influencing everyone's outcome in terms of how they do things or what they do.
Well,
so when you say within the context of science, when you say
their ideas about science, that influence how they go about what they do.
You mean, are there scientists who have some sort of a different philosophical bent? And if they have a certain philosophical, no, it's too. It doesn't. It doesn't lend itself to that. There aren't really different. It's not as if you have. Scientists might say that, that particular group really they're really numerically bent. They want to model everything and compute everything. And so their philosophy is different to somebody else who says, I'm not really interested in numerical computation, whatever. I am interested in physical observables. So I think there are obviously then different characteristics that would lend somebody to being an experimentalist versus somebody who's a theorist or somebody who's doing calculations, that sort of thing. By and large, those that are doing experiments tend to want sort of fairly concrete results, and they're often they need to be actually fairly good with their hands in the lab. There's just general skills, no matter what it is, whether it's molecular biology or chemistry. You've got to have a mindset that when you're in the lab, it's not. Yes, sometimes you go to the lab, you say, I'm going to do this experiment. And you plan out what do you need, what chemicals, what equipment, and you do the experiment. But whenever you're doing an experiment, things happen. And if you've got good lab technique, you have a good skill set, you go with the flow. And you go, well, wait a minute, and it's on the spot. You go, well, that's a little different, I'm going to have to do this now. And then the outcome is a little bit different from that step, so now I'm going to do this. And you take a different pathway that will be a fruitful one if you have good common sense. And as an experimentalist, some people have a sense in the lab, and others that seem to go around dropping things, and they do a whole lot of experiments, and they're not meaningful experiments in the sense that they're going to give a clear answer to what the question is. And if you don't design the experiment carefully enough, you're not going to have a clear answer. And if the answer isn't clear, then you've wasted a lot of resources. Because a characteristic of science is to say that when you are studying something, if you're an organic chemist, the objective can be to produce a particular molecule, and that's your objective. But other times, if you're doing more research and discovery, i.e. trying to understand the biological pathway, then you really got to, because you don't know what the outcome is. You don't know what this biological pathway is. Like, for example, citric acid cycle, or the Krebs cycle, or the breakdown of ATP, or the synthesis of ATP in a biological system. You're trying to figure out what are the enzymes involved. You've really got to be open to unexpected outcomes, because you don't know. You just have certain skill sets that'll help you through the labyrinth of what you're going to stumble across. As opposed to somebody saying, well, I want to design a particular molecule, this type of structure, and they're going to have different skill sets that allow them to get to that goal, but they know what their goal is. Sometimes that particular molecule might be too difficult to synthesize, and they end up synthesizing something similar, but still that's their goal. That's goal-oriented research, as opposed to this sort of search and discovery. But I don't want to say it sounds like walking along the beach and all of a sudden you discover something. It's very much goal-directed on a day-to-day basis. But if you're dealing with, as I said, a good example would be a biological system, don't ever pretend that you know what you think you're going to find, because it's probably going to be quite different. Unless there's just so much known about that system, all you're really doing is finding out one step. And you know the step before, you know the step after, and you're zooming in on what's happening in between, then yes, that would limit the number of possible outcomes. But even then, it's not the same as somebody saying, I want to design a building with these features, and then asking people to design it and build it. Because that's a goal-oriented object, and it might, it will have a whole lot of very high skill sets, particularly engineers, maybe new materials, very creative architects that are stable, etc., because these structures are unusual, the buildings are unusual. As opposed to, I said, somebody who is really trying to figure out what is a pathway of a particular, let's say, the life cycle of an organism. Maybe it's even a virus, or a pathogenic bacteria or something. That you would have a different, people say that's almost like a different philosophy in terms of how you go about your experiments.
So, how do scientists come up with their ideas? Do you want me to?
Again, I think if you just, when you're talking about a particular experiment, they're reading other papers in the field, and they're getting ideas, and they might have a particular idea in mind. As I said, some research is very goal-oriented. Somebody could be trying to synthesize a drug for malaria, and they have a particular set of skills in terms of synthesis, but there can be other types of synthesis that might be better or worse, but they don't have that skill set, so they're going to use their skill set and their knowledge, their ideas, to get to a particular objective. They're going to synthesize that molecule, and then it's going to be given to a clinician who is, and of course there'll be feedback between the clinician and the clinical studies. There'll be some preliminary studies before it gets to any kind of human clinical trials, of course, but there'll be feedback, and yes, it looks like it'll kill a particular pathogen, but at the same time we think, at least certainly in mice, it has these really bad side effects. What can we do to modify the structure to make it a better drug so it is less toxic? but still perform its function of killing the pathogen. So in terms of the day-to-day basis, it's by and large it's occurring perhaps more on the scale of week to week, and it is looking at what is known, starting with what is known as the scientific literature, and then thinking about it yourself or discussing it with others in your research group or with colleagues, and then following through collecting data and then analyzing the data and then seeing, well, does this data suggest that this is the compound we set out to make? Nowadays that kind of question is very concretely answered with the techniques that we have. So and they would soon find out, oh no, it's different, and they would then have to pursue different conditions to get the molecule that they want to synthesize for some reason, whatever that reason might be. So it's feedback in terms of what data they're getting and is it working. If it isn't working, we need to try something else. So in synthesizing a molecule, I've picked this example a couple of times, but it's a very specific goal to let's say a particular hormone, insulin, for example. Thousands of cows had to be slaughtered, which they would have anyway, at least for meat, but at least then the gland had to be taken out and you get this tiny amount of insulin. So insulin was not available for diabetics. But once the structure of what was known to be the thing in this thing that would turn out to be insulin was playing the critical, that's what was needed for people who were diabetic. And then the structure was known. Once you knew the structure, if you can synthesize it, you're going to make it a hell of a lot easier than having to kill animals and from kilograms of say animal tissue, end up with micrograms of a drug that few people could afford.
Right.
And so you then go about ways: one, figure out what is the compound; two, what's its structure; three, can we make it?
Yeah.
And if you can, then you've got a very useful drug, and that is a natural structure that is now synthesized and produced. That's very much goal-oriented. But everyone on a day-to-day basis or really week-to-week basis would be, what do we know? What is it that we want to know? And how can we go about efficiently finding out what we want to know?
Thank you. Could you explain to me what a theory is?
It is a conceptual model that is self-consistent with what we know.
Right.
That is what it is.
Okay.
What is it that we know? Well, hopefully it would be, again, unless you're talking some of the more exotic branches of science, the high energy physics or astrophysics, some of those things are not testable yet. Okay? But by and large, most of science is. So, if you're wanting to validate a theory, or refute it, or modify it, you ask yourself a set of questions. You say, would this experiment give insight as to whether this theory or model is valid or not? And if you believe it will, then you go and you do those experiments and you get that data, and then you make sure the data is valid. You get some unusual results, you want to verify and verify and verify, and if it's good, if the results are unexpected, and if you're getting self-consistent results, then you comment on how that does or does not fit into the prevailing model or theory.
So, if a scientist has a theory that influences their ideas about different experiments,
has a theory about influencing the outcome of the experiments?
No, if they have a theory, if they subscribe to a theory, does that influence how they look at different experiments?
Oh, completely.
Okay.
Within the context of everything that I've said, it is all subjective.
Okay.
It is all subjective. Within the context of our entire interview here, I'm saying, what, of course, the personalities involved are going to play a tremendous role, but I don't want to give the idea that that science, because there is sometimes in general society this feeling that well, do we really know anything, or science doesn't work. Insulin works. You have a minor infection, well, before antibiotics, you might lose that hand or that arm, or in fact die. Nowadays, you get a minor infection, not a problem. We can purify water, etc. So science does work, and it doesn't belong to any one person or group of people. It is a philosophy, and that philosophy is one of questioning. But when you take it at the grand scale, and that's what I've been talking at, the overall, because you said, well, what is science? So
right.
I'm not, I could go into detail in terms of what science I have done or am doing. I haven't done that, because that's not relevant.
Right.
But in terms of individual personalities, yes, absolutely. There can be somebody who realizes, wow, that experiment was really a bad experiment. And, are they going to run around telling everyone? No. Are there going to be opinions in terms of which experiments were perhaps more influential in tying into or verifying or not validating a theory? Then people being egocentric will obviously say, well, of course my experiment, my papers contributed more than so-and-so's, but perhaps not as much as so-and-so's. But somebody else might say, well, actually, I don't see it that way. I think mine's a little higher than yours. And so in that context, yes, there's the usual subjective opinion in terms of how important that work is to its contribution. That's, of course, related to importance. Yes, their interpretation. But again, you can't take it to the extreme where you can say, aha, well, since science is done by people and people have inconsistencies, let's put it that way, how do we know then that science doesn't have inconsistencies, right? That there's a whole lot of this other stuff that's actually it's all bullshit, all bogus, right? And the answer is because the nature of science is such that if something is inconsistent, other people are going to see that, and it's going to fall by the wayside. You see, you can't have somebody saying this is the structure of DNA 40, 50 years ago, 50 years ago, and then me coming along and saying, well, based on that structure, I'm going to do this, and I'm going to get funding and have a whole lot of people devote several years of their life, including mine, and it doesn't work. I'm going to be a little put out, shall we say, okay? I'm going to say very loudly, I based it on this. and my outcome is not self-consistent with that. I'd have to first check that I'm doing my experiments correctly, but assuming all the methodology is fine, and I'm not making some mistake, or the people in my lab, etc., or the people I'm collaborating with, I'm going to criticize that and say, I wasted 2 years trying to do something that really wasn't possible because it was based on this and this, and somebody else is going to say, actually, I also found the same thing, and I stopped working on that, or whatever. So the things that do turn out to be as best a representation of what we understand that thing to be, and by that I mean nature, that molecule, whatever it is, that disease, etc., it will gather momentum. And the things that are wrong are not, with time, gather momentum.
But if you have two people who are coming from different theoretical frameworks, would they look at an experiment differently?
Yes.
Okay.
Yes, they would.
Yeah.
They would. And hopefully the benefit of that would then be even more fruitful understanding. So that if somebody really has specialized training with a particular viewpoint, somebody else has very different training, but they're both tackling a very similar problem or even the same problem, at one level their outcome might seem quite different, but then that will be the challenge of others who read it, to reconcile these differences and to reconcile those differences and put them into a self-consistent framework, so that what was originally looking like two very different interpretations of something ends up being synthesized into a larger, greater understanding. And of course, that is what theorists are doing. Many theorists are doing that. That's one of their main objectives. So, for example, there are different types of forces: the forces between charged particles, the forces that are to do with very large bodies, gravitational forces, and linking. Is the relationship then between the charge attraction or repulsion, let's say it's repulsion between two electrons, and forces that we see at much bigger length scales, and weaker forces like gravitational force. Is there in fact a deeper theory, if you want, or a theory that will accommodate, which at one level looks very different, but put them into a self-consistent framework? Absolutely, sure. That's very much that's what theorists do as well. So I didn't mention that before, but it's healthy. You see, that's the framework that science thrives in. The framework is that you do have different opinions, and you do have different viewpoints, and those viewpoints need to be discussed, and sometimes there's disagreement, and then sometimes there's a half agreement or 10% agreement, or whatever it might be. But then people will try and refine those ideas, and others will then try and test them, and further, either corroborate them or move on to something new. If it's not working, if something doesn't work, they might not go around saying it didn't work. They'll just automatically move on to something else. Okay. And so that's how the things that work, and by that I mean self-consistent, because I don't want you to think, you haven't, none of your questions have pursued this, but concepts and models in chemistry and physics, by science, they are self-consistent, okay? Or they're refuted, or we wait to sort of see, well, we need more data, etc. Or they're refined in more detail. But I don't think there's only one model that is self-consistent with the interpretation of the data. It is possible that one can have a radically different model that would still be self-consistent with experimental observation. It's a bit like, what I'm getting at is, it would be the equivalent of somebody saying, I know English and only English, and therefore the only way to communicate is through English. And that's just not true. Because even though there are these other languages which I have, or an individual has no comprehension of what these two human things are talking, they're making these noises, this completely foreign, in no way is it making any sense. Yet those people are communicating, and they're communicating about the world about them and what they're going to be doing, and their emotions with each other, etc. At the same level that my language allows me to communicate with other people, etc. So therefore, those two languages both have the same outcome. They facilitate communication and comprehension between people. Yet they are very different in their structure and in their details. And you cannot then say, well, one is better than the other. They are just different. And that can certainly be the case in science. I would not be so arrogant and to say, and I think many scientists would disagree on this, to say that our model is the only model. By that I mean fundamental things, even though I teach it and research, etc. That atoms and bonds, etc. You can have a very different model that will be self-consistent with experimental observation, but the model could be very different. And I'm not saying the model would be better or worse, it would just be different. The main thing is that, just like with a language, I can construct a new sentence, a sentence that's never been constructed before, but it is still comprehensible to somebody else who speaks that language. There is no, in 500 years' time, it's not going to be in 50 years' time or 100 years' time, but maybe in 500 years' time, our models of things will be very different. Just like if you were to take, there was science 500 years ago. People here wouldn't actually perhaps call it science, but there was the process of discovery and interpretation, etc., 500 years ago. And those models were helping people understand their observations, and that's what we're doing now. And in 500 years' time, the models, I'm sure, will be quite different. But if one were to take an alien, just to give an extreme example, take an alien species, come here, make a whole lot of observations in terms of the wind, the ocean, stars, matter, chemical, getting down to chemical bonds, whatever. They won't call them chemical bonds, and they might have very different models to describe the phenomenon, but they will still have an equivalent understanding to what we have, to the extent that they can synthesize a molecule. So I can take concrete examples. They could synthesize a molecule, and we can synthesize a molecule, but our conceptual understanding of what it is we're doing to synthesize it could be quite different from theirs. And I think a lot of scientists might be a bit wide-eyed by that statement and say, no, there is this model, and it is this. They take very concretely that this is the model, that this is how nature functions. And I am not in any way so arrogant as to suggest that we really do know what nature is. We can have descriptions and saying, well, here's a model to describe a bond. Whether it is actually that, I would say no. It's just it's self-consistent, and it leads to discovery and comprehension. That's fine.
Okay. We talked about this. I think you mentioned this a few minutes ago. about experimentation and results, but if a scientist does an experiment and gets a result that he or she doesn't expect, is this a bad result?
Not at all. It can be, in fact, there's so many answers that come to mind there. It can be because you want to do things that are exciting. By and large, I mean, you don't really want to jump out of helicopters every day, but by and large, right, the majority of people don't want to be doing the same thing all the time. And so, if you're doing science that, if it's predictive, then if it's that predictive, it isn't really science. Okay. Because I would say if it's that predictive, then you're not really. This is going to sound arrogant, but you're not doing worthwhile science, because science is supposed to be a discovery process. And if you say, well, this is what we expect, and then you do the experiment and you keep on getting that, well, okay, so you've confirmed that you understand something, and you've confirmed that that model is the correct one. But many models have been, for so many years, verified, and for example, the technique of X-ray crystallography for solving a crystal structure. I don't need to solve a crystal structure using X-ray crystallography to prove that it works. There are millions of structures that have been done. Okay, so that's what I'm getting at. That would be a training exercise if you keep on going into the lab and getting the result you expect, because you must be doing things that are very, very mundane.
So are you saying you can learn from an unexpected result?
Absolutely.
Okay.
Absolutely. In fact, sometimes that can be the only way to learn from an unexpected result, because, as I said, if you're always getting, science is, it sounds like, oh, well, we know what we're doing, and, I'm saying to the outsider, the so-called scientist, okay, that somehow you always know what you're doing, and therefore you just go into the lab and say, well, we're going to do this, and that's what you get. That is not the case at all. I mean, certainly, if something has been done before, and you're going to repeat, i.e. you're a pharmaceutical company and you're wanting to make aspirin, well, yes, you're going to go into the lab, you're going to say, this is the equipment, these are the chemicals, and you're going to say, this is our object, this is what we expect, and you're going to get that outcome, because it's been done before.
Right.
So, your implied question is that if you are doing something new, then how could you possibly know the outcome? Right? Okay? Right. You see what I'm getting at?
Yeah, absolutely.
So you cannot really know the outcome. Now, to be fair, I mean, I'm not, I think, what you're saying is, I mean, the wording has to be careful here, is that there are certain options. You might be expecting a variety of outcomes, because you're doing new research. You're not just going to be repeating something that's already done. That's not research.
Right.
Okay? So you might, as a scientist, have a range of ideas in terms of what you're expecting, and the results will fall within that range. And but there still can be a fairly wide range, and then depending on what the outcome is, you'll take the next step and say, okay, now I'm expecting this range of outcomes. And if it's this, then we're going to do that, and if it's this, then we'll try that. But sometimes I think what you were getting at is that you're expecting a range of outcomes, and it's not like any of them. It's all, right? You need to be very careful there. Was the experiment done right? Was it done within the constraints you thought it was done? If it wasn't, you first got to do that.
Right.
Because otherwise you're chasing your tail. There's too many parameters. You think that something was done a certain way and it wasn't. In which case, the outcome is going to be different. So you've got to, and of course I'm talking within the context here of an experiment. So you've got to make sure that that it was done right, and that the person who was doing it did it right. But there wasn't some simple error that was unnoticed. So you've got to be careful of that. But if the experiment's done a couple of times and you get the same outcome, and if it was a random mistake, very unlikely to get the same outcome. Therefore, if it's a real important question you are asking, and you're getting a very different answer, that's great, because now you're getting something that's unexpected. And that's going to test you in terms of trying to figure out what's going on. So now we're into the realm of new, right? Because that's discovery. That's when somebody has already gone to another coastline, and they're coming back to that same coastline. That's not discovery. If Christopher Columbus says he doesn't know if there's going to be land or sea, that's discovery, right? That's new. So
that's what you learn when
that's what you learn when you have unexpected outcomes. You learn, and you are challenged by it, and then you have to use your skill sets to figure out what's going on. And that's really is to a large extent of that is really what science is about. It is not. If everyone knew the outcome of what they were going to do, that wouldn't be discovery.
Yeah. Okay. Thank you. So if you're going to do an experiment to test an idea, and would you do an experiment that might prove your idea wrong? Would you set out to do?
Let me be more concrete. You mean I've published several papers saying this is an idea hypothesis, and I think it's great, and I think it's self-consistent, and now I'm going to set out to destroy it?
Yes, or would you either that, or would someone do an experiment that had the possibility of completely proving?
I think yes, there are those that will. I mean, I think I think again that boils down to the personalities. They might want to move on to something else, but if they say, gee, I just realized there's one critical question, and I didn't ask that before, and now I realize it needs to be asked. And if you go ahead and do that, and it turns out to be a really critical, a very important question, then actually you really want to do that because you'd prefer to be the one that stands up and says, or publishes, meaning, I reevaluated it. In fact, this was a critical experiment that needed doing. I've done it, and in fact, the outcome is not what I was expecting. But then you would really want to say why, and you sure would prefer for you to be doing it than somebody else.
Is that just for saving face, or what?
No, I think it's going to vary from character to character. There can be, somebody might have had funding to do a particular thing. They did it. They're now working on a different project. They then realize, oh, wait a minute. 5 years ago I was working on this other thing, or even 2 years ago, but the people who are working on that aren't here, and I've got funding to do something else. It is actually illegal to use funds that are for a particular research project and use them on something else. Okay? And this is where funding can have some really negative effects, right? Goal-directed funding can be very negative because this is what's been justified, and this is what okay. So now you've got to say to yourself, okay, I'm going to have to allocate some resources to this. Maybe you do that. You say, no, it's too important. I'm really uncomfortable. This could be an important thing, and I want to focus on it and get it right. Okay? Somebody else might say, it's really not such a big deal, and it's in the back of their head, but because they don't like it, they kind of go, I'll just focus on what I'm doing. Or the person might say, I really want to work on it, but actually I'm restricted right now. Funding hasn't been as good as in the past. I've got very specific funding. I've got to use it for this. If I have time, I'll get back to that. And maybe they do, maybe they don't. Maybe somebody else does it, that particular experiment. And, it's an embarrassing thing. And they might even communicate then once they hear about it and say, you know what, absolutely, I did think of that, but we didn't do that, and we should have, and it's a very interesting result. Or the person can start fighting it, right? And say, well, you did something wrong, your experiment's wrong, and blah, blah, blah. What happens is a coin toss on a variety of factors. The person's character, how the other person does it. If they do it in a reasonable way, they might even contact them before they publish it and say, you know what, we're getting a very different outcome here. And the person might say, well, you know what, I was planning on doing that, and I agree, it could be interpreted this way. Maybe they'll end up being both on the paper. The person might be as generous enough to say, look, I'll be first author, but you are the one who really advocated this, and this work is going to be saying it might not be the case. are you going to agree with what we're finding? And if they're part of the paper, of course they're saying we're agreeing. Very nice outcome for everyone. Okay? The person who doesn't have the resources anymore is now part of a program, a research program that does have the resources. They're getting interesting results. You've suspected that might be the case, but you haven't been able to return to that line of research, whatever. Or person says, you publish that, I'm going to destroy you.
Wow.
And that can happen too.
If you have an idea about something and you do a test, what happens to that idea once the test is done? Does it change? Does it...
Well, again, if you're doing research, the test ought to be something that contributes. It can't be just confirming what you already know.
Okay.
So if it's research, it has to be something new. If it's something new, then it has to contribute in some way. Even very small, but it needs to contribute in some way to that whatever it is, that area of research, etc.
So if you have an idea about something and you do a experiment, are you more sure about that sometimes or less sure?
Absolutely. The more and more you focus on something and you get results, and other people say, wow, these are really nice results, and they're published, and other people reference your work and say, well, this work has led me now to go on to do this work. So they're acknowledging that this was a step in terms of what they're doing. Then yeah, sure.
And you just spoke a moment ago about scientists changing their mind about something. You know, we were talking about the someone who says, "Oh, I should go back and test that because now I'm thinking it's going to be different." When do you change your mind about something?
Well, it's going to be a subtlety. I mean, it's not like. I mean, it would be a bad science. So let me perhaps clarify something. There's a difference between wishing you had done a particular experiment and not doing it at the time. That's what I was really talking about. And then you realize 2 years later, you get some insight. You say, well, actually, I really should have done this experiment, and that would really be interesting. Perhaps you do it as limited as that, and somebody else does that experiment, and it doesn't really fit in with what you thought, or your publication of 2 years ago. First of all, that publication of 2 years ago isn't just wrong; it's contributed. Why? Because the person read that, came to the same conclusion that you've come to 2 years later, realized that there was a gap in the logic. They've probed it, and they've got a result. That's a contribution.
Right.
But that is, and so that is both papers are contributing to the other person's understanding and facilitating them in asking that question and pursuing it.
Right.
If, on the other hand, you're talking about a paper where somebody just does terrible experiments and they can't be duplicated, then that paper should not have been published. That's a negative paper, and that's bad science.
Right. I think maybe I didn't make it clear. I was wondering about when scientists change their minds, how that happens. Like,
I was just clarifying earlier on. Yeah, so I was just clarifying earlier on.
Okay.
In terms of, you mean when?
Or how? What's the process? Like, is there something that happens particularly if you have like something you think is going to happen or you're interested in? How
you would perhaps be reading or at a talk where it's not really directly related to what you're doing, but you gain some insight and you realize, wait a minute, either that technique I could use, or that technique might answer a question that I didn't realize should have been a question, or it might be just a conceptual understanding. Oh, I didn't know that if you did this, you could find out about these properties, etc. And so you're going to go back to the lab, and you're going to say, well, I need to think about it in a slightly different way and do a different type of experiment. and use maybe different equipment, and see what the outcome is. Okay. In terms of your question is, when do they decide that they need to reevaluate something?
Yeah, or I thought maybe more at what point in the process of investigating ideas or doing science. Is there a specific point maybe that you change your mind after something happens? Is there a specific instigating factor for?
No, I'd say there's all sorts of things.
Yeah.
I mean, sometimes you set out to do something. You've collected a whole lot of data. You then, many months later, because it takes that amount of time to collect the data, do the experiments, you then analyze the data. And at first, it's not really making sense. Okay. Because remember, you're not repeating what somebody else has done. That's not really research, right? You're doing something. So you're trying to grapple with this data, and also your skill sets might be in the process of still needing to, shall we say, grow. Okay. So you haven't done perhaps that type of experiment before. So you're trying to figure out something, and in the process of trying to figure out the interpretation of what's going on, you see something, right? And you go, well, that's interesting. I didn't know that was the case, or is that really valid? Am I understanding this correctly? That's usually, I think, part of the first process. Do I really have this right? Is that really? Is my thought process self-consistent with what would others think the same as what I'm thinking if they saw what I'm seeing in terms of the data? And then you might have set out. I mean, I did my master's. Actually, it was a lot of experimental work. Could have been a PhD, but my objective there was really one, to learn a technique to get a skill set, master student, and it was with X-ray crystallography. And I was going to answer a question, and that question was, what are the selective properties of a particular host? A host is a type of molecule that forms a structure that allows other molecules to sit inside it. The molecules that sit inside it are called guests. The main structure is called a host, just like it's their house, they're the host, and guests come in. Okay. And I was going to set out, using this technique, for a particular molecule, a particular host, to answer what are the selective what are the properties that this host selects for. Now, crystallography was considered to be the perfect technique for that. Ideal technique, at least I thought so. And I did a lot of experiments, and I got a lot of crystal structures. That alone is very fruitful, okay, very productive for a master's thesis. I then solved those structures, very fruitful. I had 8 of them. This is a long time ago. Doing structures then was a little harder, okay. Turns out that the molecules were disordered inside the structure. It means they didn't sit in one place. They moved around. They were disordered. Well, that was a pain because it made solving the structure difficult. Okay, it's a bit like having guests in your house. You don't know what room they're in. Okay, you don't know where they are, so it makes it a little difficult to understand then the host-guest interaction. But anyway, I did that. I was able to more or less solve the structures with these guests. But the underlying question is then, well, why were they disordered? Well, they were disordered because the interactions weren't particularly strong. So if they were strong, they would be located in one position. They weren't that strong because they weren't located in one position. They kind of shifted around a bit. They were disordered. Crystallography couldn't answer the next question. What are the selective properties? Because it turned out there was, but you wouldn't be able to determine using crystallography because crystallography requires knowing the position of an atom. That atom needs to be stationary. If that molecule inside is not in one fixed position, it's disordered. Crystallography can't answer that question. For me, I thought I had a whole lot of useless stuff, right? I had all these structures, and I thought it wasn't answering the question. Turned out the technique had its limitations, because if the interactions are weak, then the guests are going to be disordered. That means you have to use a different technique. So that one technique can't answer all the questions. There wasn't anything wrong with what I was doing. It was just a limitation of the technique. but there are still there's still a lot of research to do with using crystallography to answer those kind of questions, and that's where you need to have more than one technique, because if the interactions aren't strong, that technique isn't really going to give you much information, and there could be secondary, that is, the weaker interactions could still be figured out, but you've got to use a very different technique.
Okay. Well, so if scientists can change their ideas, do they ever change their whole theories?
No, very unusual.
Oh, okay.
It happens very rarely. It does happen. I mean, it does happen, but it's very rare.
Why do you think that is? That it's so rare that they change?
Because you've got to have such a shift in conceptual understanding that the vast majority of science is exploration of a fairly well understood area of science. It is rare that. Let me give you an analogy. If you were going to a new continent, let's say it's Africa, you would discover the Nile, okay? This huge river, very long river, very important consequences for the people who are living there. You're coming, at least when I say discover, from your culture, you're coming, you discover, okay? For your culture, it's a discovery. And you discover it now, and you find all this rich growth and other people living there. That's a major understanding. Maybe that river's running north-south. All the rivers in your country and the countries near you are running east-west. This river runs north-south. That alone would be a big realization. Rivers can run other than east-west. But now the Nile's discovered, okay? But you're an explorer, and it's 100 years later, and you're still exploring parts of the Nile. It's fine. That researchers find it or whatever. And is it likely that you're going to come across a structure as big as the Nile? No, not possible, right? The big thing has been discovered. You are understanding small ecosystems within a part of the Nile, or smaller rivers that are a result of the Nile, or that so that feed the Nile, whatever. But are you going to have this new paradigm? Rivers can go north-south? No. So the majority of research is the Nile's already discovered. Right now, there's thousands of people exploring the Nile. It's big. There's a lot to discover. There's a lot of detail, different ecosystems along, etc. So that is the bulk of science, and it is rare when there is a something that really changes. You were saying, a whole change in model, right? That's a radical shift. A radical shift is, since you're in education, it is our understanding, without any models, that a baby learns language by hearing their parents, interact with them and talk with each other and talk with other people. Baby just soaks it up. Okay, it would be an astounding outcome if somebody were to prove that babies don't get language by osmosis, by just being in the environment, that actually there's a genetic program that switches on. Okay?
So a theory has to be that big. How big.
Well, I'm just giving an example because I think, I'm just giving an example of when you say a model, I mean, are you talking about like the basis of bonding between atoms? If somebody comes up with a very different model, that's going to be a major overthrow of a previous model. It can and it will happen. Our understanding of bonding will change. But is it going to make the previous models incorrect? Highly unlikely. Because those models have been refined with observations. millions of observations. How could they be all so wrong? Okay,
so
but is it more likely to refine it? Yes.
Okay.
Is it likely to give a greater understanding? Yes. But so I was giving an example of a more example where somebody says, "Oh well, science, tell me about under these models, and then this one gets overthrown and it's wrong." No, it gets modified, deeper insight, that sort of thing. That's really and you're as an individual involved in science, you'd be very fortunate to be part of that. That you would be part of a process that really gave rise to a very clear break, very clear, oh, well, not that that was wrong, but this is way more, gives us way more understanding and predictability in terms of now we know by using that model we can understand bonding to a far greater extent than how we understood it before. So, for example, if you come up with a model where it is self-consistent with a baby acquiring language from hearing their mother and father and their siblings, if you came up with a model that refined that, still took that as that still holds true, but and then there's a whole lot of something that gives a lot of insight as to how it occurs or why it occurs, that sort of thing.
So it would refine the theory.
Not necessarily overthrow it.
Got it. Thank you.
And again, I want to emphasize that Newton's laws are not wrong. People say, "Oh, Einstein's laws refuted Newton's laws." They didn't. They're a set of laws that are applied to a slightly different situation. Not slightly different, very different situation. So the movement of a baseball is the same now as it was described by Isaac Newton. Or the swinging of a pendulum, or based on the motion of everyday objects. Einstein's, and I don't want to just pick Einstein, but all the people of that time, of that revolution of quantum physics, they weren't dealing with the movement of baseballs and pendulums because those equations work, and they still work. They moved on to something else, the motion of atoms and electrons. There, Newton's laws didn't apply, they didn't work. Came up with new equations, quantum mechanics, movement, quantum, small, the movement of small things, atoms, molecules, electrons, that sort of thing.
So just two more. Thank you so much.
Okay, what time is it?
It's 3:15. Is that are you?
I have to pick up my wife at 3:30.
Okay. Well,
so,
do you have time to give quick answers to the last ones?
How many more questions are there?
2.
Okay, let's do it.
Okay, thank you so much. Do scientists always achieve their goals? Why or why not?
No. Because sometimes they realize, for very practical reasons, their goal wasn't even the right goal. Remember, it's a discovery process, okay? It's a bit like somebody not knowing that there's even land out there, and yet they're going to have this goal of finding land, and not only that, but they want a lake right next to the piece of land they find. It's not going to happen, right? They'll be fortunate enough just to find land.
Right.
Or a palm tree that looks just like the one they got at home. If you're going to new territory, you're probably not going to find a palm tree.
Right.
And so what I mean by that as an analogy is that no, often the goals you set out with are not the correct goals. And in refining, you in getting data and pursuing it in more detail, you realize, that isn't the outcome, and you've got to go. Remember, this isn't as if the worst thing. I mean, you definitely don't do science by pronouncing to everyone, "These are my goals," and then you set off, and because it's not working out that way, that you somehow twist the facts and the data to fit your goals. That's not science.
Right. So scientists can be wrong and make mistakes.
Absolutely. Critical part of their work. Happens all the time.
Okay. Great. that was the last question.
Okay.
Thank you so much.